Okay, so in this video, we're gonna go over the rest of the problems. And on the review sheet, let me share my screen. I think we stopped at 29. All right, so hopefully you can see what I'm seeing here. Let's see, so yeah, 29. So the next one is 30. So it says the graph, you have this graph of a function given on the left. And then we're given the graph of the function on the right. And we want to determine what, so it's clear that this graph right here has the same shape, so it's reasonable to expect that this graph right here is some sort of translation of it, and it is. It's going to be translation of the original function. So we got to figure out exactly what sort of translation though. So the easiest way to do something a problem like this is just to pick a single point and track where it moves. So these transformations are rigid transformations. So this is going to be some sort of vertical and horizontal shift. So if you know how one point moves, then you know how all of the points move, and that'll tell you in general what the function, how to write down the shape or the form of the function algebraically. So you have this point here. This is the easiest, probably the easiest point to to keep track of. So it goes from being here. So we can just mark it over here, and it goes over 2 units and then up 1 unit. So over to the right 2 units means you had to take the x and subtract 2 from it, and then up 1 unit means you have to add the 1 to it, shift it upwards. So that would say, I guess that would mean A is the right answer. Yeah, A should be the right answer there. So here's a find the inverse. We actually already went over problems. So you can see there's quite a lot of problems that are similar. So like there's gonna be only probably one of this kind of problem on the final. So yeah, there's a lot of problems in the review. But I don't think the review is gonna be, I mean, I don't think the actual final is gonna be this long. I don't have the final yet. I just emailed um my the calc coordinator about it, and hopefully I can get a copy of it. And then I can kind of maybe, if there's maybe, especially if there's stuff that we haven't really covered, I can maybe make another video or something, do something to explain those topics that we didn't like cover as in depth. Because I judged other material to be more important. All right, so let's go over this problem though. So remember the steps for um there's like 3 steps to finding the inverse of a function. So you're gonna set y equal to your function. So y is gonna be f of x, which is equal to 8x cubed plus 5. And then you're gonna swap or replace x and y. So when you do that, you get x is equal to 8y cubed plus 5. And then the last step is to solve for y. And whatever y, you're going to get something like y is equal to some expression involving x. Whatever that expression is, that just is the inverse. So the easiest thing to do would be to subtract 5 from both sides. So you're going to have 8 cubed, 8 times y cubed is equal to 5 minus x. And then you're going to divide by 8 and then take a cube root. So you're going to get the cube root of 5 minus x over 8. And so this right here just is the inverse. So this implies that f inverse of x is equal to the cube root of 5 minus x over 8. All right, so that's that problem. All right, so for the next one, we want to solve for x. And you just need to recall that what is it what does a logarithmic equation mean? So log base a of x is equal to y means or is equivalent to that when you take a and raise it to y, you get x back. That's all that means. So the logarithm is the power you raise a to get x. So that's all that says. So we have this equation right here, log base 2 of 3x minus 2 is equal to 2. And by definition, I mean, this is an equivalence, if and only if, you have 2 raised to the second power, so 2 raised to the second power is equal to 3x minus 2. And then this gives you 4 is equal to 3x minus 2. And then this gives you 3x is equal to 6. And finally, x is equal to 2. You divide by 2. All right, so we now, for the number 33, we're given two functions and we want to find their composition. So there's these two choices. There's this choice right here. This one's going to obviously just be outright false because this is the product of this function and this function. And composition is not the same thing as multiplication at all. I don't think they're ever honestly the same. I don't think let me see. That's actually an interesting question to determine. Here we go. Question. For what f and g is f composed g equal to f. So this is composed. This is times. I don't know. That's an interesting question. But anyways, so I feel like this is probably never true, or like true, and well, f and g are really boring functions. But anyways, my point is, f composed g and f times g are almost never equal. I honestly can't think of any examples where they're equal. So don't confuse the two. I know when I was first teaching this, and I gave some exam or quizzes on it, some people confused that. They confuse that. So f composed g is, remember, by definition. So you plug x into g and then plug that into f. So it's f of g of x. So that means we're gonna take 3 minus x and put it in the place of this x right here. So it's gonna be cube square root of 3 minus x plus 2, and then I guess you can simplify that further even to get 5 minus x. So the right answer is gonna be C, not A. Definitely not A. And you can see it's not B or D either, but definitely not A. This is really very wrong because it's the product of the two. And in general, that's not composition is not the same thing as multiplication. All right, so we want to find the domain. So first of all, we have on the one hand, we have that x cannot be equal to -3, and we get that from looking at the denominator. On the other hand, though, we need 2x minus 6 to be greater than 0. So we have when you solve for that, so this is equivalent to x being greater than 3. You can see that. So you initially you need these two conditions right here to hold because you have this log of 2x minus 6, and whatever you're taking the log of has to be positive. So that's why we're setting this greater than or equal to, or sorry, greater than 0. We also need this condition from the denominator, but it turns out this actually ends up being redundant, right? Because if x is strictly greater than 3, then it can't be equal. Well, if it's strictly greater than 3, then it's definitely not going to be -3. So this is meant to confuse you. You don't need that. So the answer is going to just be 3 to infinity. So that's this is going to be is the domain. And just to recall the first fact, just in general, let's say log base of say g of x is defined if and only if g of x is positive. So to figure out, so if you're taking the log of some function, log base a of some function, it's defined if and only if the function is positive. So in order to find out where the log is defined, just find out where the function is positive, and that's exactly what we did over here. And this condition ends up being redundant. All right, so for this one, we need to, well, I guess the easiest way to do this, so it may not be obvious at first, which um um of these we're asking what of these which of these identities actually holds, and so it might not be obvious. This is we obviously want these to hold, like maybe say for all x. Um, so we have to figure out which one holds for all x. Holds for all x. So the best way to approach this, to notice the left-hand side is the same in each option. So just use the laws of logarithms to compute to maybe break up or simplify the left-hand side and see what you get, and then you'll know which identity is true. So we have a product here, and then so the product becomes a sum. So ln of 2 plus ln of e to the x plus 2. And then remember, ln and e are this exponential function are inverses of each other. So the ln and the e cancel, and all you're left with is ln of 2 plus, and I guess you could put this in parentheses if you want, x plus 2. So it's clear then that what we have that holds in general for all x is this one right here. And a should not be true for all. Let's see. Let's see, why is oh well, this one D is not gonna be true. Let's try to rule out the other ones. So D is not gonna be true because um the natural log function, there are values of x for which this is negative, but notice this side right here is always positive. So D is definitely false. This cannot be true because the left hand side can be negative, but the right hand side is always non-negative. As for this one, let's see. I bet you probably okay, so why is B not true? Let's plug in x is equal to -1. I think that's gonna break it. So on one hand, you have ln of 2 to the e to the -1. Oh, sorry, no, just 1. E to the 1, and that becomes ln of 2 plus 1. So that's computing the left hand side of B. On the other hand, when you plug in -1 here, you get 2 ln of 1, and ln of 1 is 0, and these don't equal. This right here, these are not equal. So this B is not true. It doesn't hold for all x. Maybe there's some x's for which it holds, but it doesn't hold for all x. Sorry, it doesn't hold for all x. Actually, let me pull up a plot. This is all extra on the side. You don't need to, but it's good to go through this because um this is like going beyond the problem, but it's good uh to go through this for practice anyways. So we want to know where does ln of e to the 2 times e to the x plus 2. When does that equal 2 times ln of x plus 2? Might not be anywhere, actually. Oh yeah. Here's a plot. So actually they're complex solutions, but there are no real solutions, meaning geometrically that the curves neither intersect. So actually this B never, there is no real number x for which this equation is true. This never true. It's true for these two complex numbers, but it's not true for any other numbers. But all that matters to rule um all that we need to do to rule out option B is just have one countersample, and we did. We just plugged in x equals -1, and we broke the inequality. All right, what about negative? Okay, so for A, why is A false? That's just plug in, I think -2 will work. So if you plug in -2, you get ln of 2 to the 0, e to the 0, so that's just ln of 2. But on the other hand, you get -2 plus 2 times ln of 2 is 0, and again, these are not equal. And let's just plug it in Wolfram. They might not be equal anywhere again. I don't know. So this shows that this helps us rule out B or A. Of course, when you're doing the exam, you don't actually have to go through each one. I mean, that would be a kind of a waste of time. Um, but the easiest way is the way to figure out which is the right option is just to do what I did. Just compute the left-hand side. Use the laws of logarithms to break it out and see what thing you get. And you can see we clearly get option C. So we get option C. But just as to go, as I said, to go further and use this example to further educate us, I want to just um, actually rule out these two options. So it looks like actually option A does have a real solution. So these curves do intersect at this point right here. It's a real number. And I guess there are no complex number solutions though. That's interesting. Let's plot from like let's see. So the solution is like a little between 5 and 4, -5 and 4. Let's do -10 and 10. I don't know if this will work. Actually, if I do plot this and this. Oh, I have plot twice. So plot. All right, let's see if this works now. Nope, didn't work. Anyways, uh, the first plot was fine. It showed us that they intersected somewhere at some real number. But the point is that it doesn't hold for all real numbers. There's one number for which this equation holds, but it doesn't hold for all numbers. All right, so number 36, we want to write this as a single logarithm. So remember, we have some convention, just to remind you. You notice there's no base here, right? No base here. So the convention is that log base, log without a base of x is just by definition log base 10 x. That's not going to matter a whole lot, but just remember, for this problem, it's not going to matter a whole lot, but it could come up in another problem. So we have 7 log base 10 of x minus 3 log base 10 of y. So this will become log base x to the 7th minus a log base 10 of y to the 3rd. So use that exponential rule. And now we have a difference of logs to the same base 10. So we can use the fraction rule. So this is going to become log base 10 of x to the 7th over y to the 3rd. Okay. All right, for this one, we want to solve for x. So we're adding 2 logs with the same base 3. So we can just use the multiplication rule. So it's going to become log base 3 of x plus 2 times x plus 4 is equal to 1. And then now you can use what this means by definition. It means that when you take 3 and raise it to the first power, you should get x plus 2 times x plus 4. But let's FOIL that out. You get x squared plus 6x plus 8, and you have 3, and that's going to imply that you have x squared. When you subtract 3 from this side of the equation right here, you have x squared plus 6x plus 5 is equal to 0. And I guess that factors as x plus 1 times x plus 5 was 0. So that implies that x can be either negative 5 or negative 1. However, actually, x equals 5, not a solution to the original equation. Because if you plug in 5, if you plug in 5 to the original equation right here, you're going to get negative 3 and then negative 1. But you can't take the log of a negative number. So the only solution is negative 1, which is fine if you plug in negative 1. So you can't plug in negative 5, but you can plug in negative 1 because you're going to get 1 here, and then you're going to get 3. And log of 1 is 0, and log of 3 is 1. So you do have that negative 1 really is in fact a solution to the equation. So remember, when you're doing logarithms, you gotta when you're sorry, when you're solving an equation with a fraction, like a denominator, x is in the denominator in some way, or if you're solving logarithms and you manipulate the equations in the way we just did to solve for x, always check that the x values you get are actually solutions, so you can rule this out. If you don't rule this out, if you took the final and you did not rule this solution out, negative 5, by comparing it to the original equation, you would lose points. So just want to warn you. All right, so now for this one, you have 2x plus 1 plus 6 is equal to 10. So now the best way to solve this is to write this equation so we have 2 to some power is equal to 2 to some other power. And that's not hard to do if you might be able to see it. We're going to subtract 6 from both sides, and we're going to get 2 to the 2x plus 1 is equal to 4. But 4 can be written as 2 to the 2. So we have 2 raised to some power and then 2 raised to some other power. So that implies, or it's equivalent, actually, this is an if and only if, this is true if and only if 2x plus 1 is equal to 2. So that implies that 2x is equal to, sorry, it's going to be just 1. And then you can divide by 2 to get 1/2. And this is the solution. I'm going to skip 39 for a second. Get back to that in a moment. All right, so we want to find in this problem one negative angle that is coterminal to this angle, given angle right here. So remember, coterminal just means, so what does it mean for two angles to be coterminal? It means that when you rotate through those angles, so remember when you rotate through an angle, you'll like rotate it, you're gonna rotate this ray through this ray. There's gonna be, you're gonna have like so let me just set it up actually. What's going on here? So you have to rotate through some angle, this is like your initial side, and then you rotate through some angle, and it determines this ray, where this is theta. And there's this point, actually there's lots of points on this ray. And what it means to for two term angles to be terminal is basically that the two rays share a point in common. So like you can rotate through theta, and then you can like keep rotating all the way around another 360 degrees or 2 pi, and you'll land right here. So in other words, the two angles, when you put the two angles in standard position, and you can actually go through the rotation, the terminal rays lie on top of each other. So, and you notice, how did we get this terminal ray? We had to rotate 300 degrees, 60 degrees, or rotate 2 pi. So that tells us in general, and so in general, an angle which is coterminal to theta is of the form theta plus, whoops, it's not plus, theta plus 2 pi k, or k, some integer k. So if k is 1, then you're gonna, the angle will be theta plus 2 pi. You can also do this with in degrees. It would be uh theta plus 360 degrees times k is coterminal. We're dealing with radian angles, but you can do this with degrees. Is coterminal to theta for k some integer. So these all your coterminal angles are of this form right here. And that makes sense because, as I said, so how do you rotate through this angle right here? So let's just, if k is equal to 1, it's going to be theta plus 2 pi, right? So that means you rotate, let's see, you rotate through this angle, theta, and then you rotate 360 degrees, or 2 pi, you rotate all the way around and you land at the same spot. But then you could also rotate another 2 pi, which would be theta plus 4 pi now. Or you could rotate another 2 pi. So that would be theta plus 6 pi, and so on. And you could, but there's no reason to think you have to rotate this way. You could also start here and rotate clockwise. So that'd be rotating with your negative angle. So and that's what we want to find. So the easiest way to do this, so I just want to, so none of this, what I just wrote is what you have to write for an answer on the exam right here. All of this, don't have to write that on the exam. This is just some background knowledge for you on what coterminal angles are, and how to find them and what they mean. So the best way to find the answer is just to take this formula right here and just plug in some negative numbers for k and see and wait until you get some negative number. So if you do take k as -1, you're going to get theta, which in our case is 7 pi over 6 minus 2 pi. Well, do we get a negative angle? Let's see. So this will be, so to get a common fraction, you multiply and divide by 6. So you get 7 pi over 6 minus 12 pi over 6. And look at that. You get -5 pi over 6. So we're done. We got lucky. We only had to consider k as -1. Sometimes you'll have to consider k is possibly bigger. So you might have to do a different k. Like for example, let's suppose that theta was equal to 17 pi over 6. And again, we had this, the question is the same, find a negative coterminal angle to this angle. Well, remember, all the coterminal angles are of this form as k varies over all integers. So if you do k is equal to 1, then that implies that 7 pi, sorry, not 7 pi, then we're doing this new angle of 17 pi over 6 minus 2 pi is going to be, well, this is going to be 12 pi, so it's going to be 5 pi over 6 is positive pi pi. All right, so that didn't work. So we need to do a bigger negative number and see if we get an overall negative angle. So we get 7 pi over 6 minus 2. So we have negative 4 pi, right? All right, let's see if that works. So if I get a common fraction, I get 17 pi over 6 minus 24 pi over 6. And there we go. Now we have a negative angle. That's going to be negative 7 pi over 6, right? So in the problem right here, we got with the angle small like this, we got lucky. We didn't have to like consider a bunch of k values. We didn't have to consider a bunch of k's, plugging in a bunch of k's into this formula right here. But you can see that if you have a large angle like this, you have to do k is equal to -1, and you'll see that you don't get a negative angle. But if you do, you have to like kind of keep considering larger and larger negative numbers. And you can imagine like if it were say like pi is equal to negative, I don't know, like 120 7 pi over 6 or something ridiculous like that, you would have to consider really big k values, very large negative k values, and maybe k would be like 10 in that case. I don't know. You can choose k as big as you want, and you'll have a larger negative angle. But in this case, we got lucky. We only needed to consider one k value. This time, we had to consider these two to get our negative coterminal angle. All right. So now we want to know. We want to do 41. So remember, to answer this, I would kind of appeal to the unit circle approach to define the trig functions. So remember, sine of some theta or t value is roughly just the y-coordinate, right? And then cosine of theta is the x-coordinate. So the problem states that the y-coordinate is negative and the x-coordinate is negative. So what's the quadrant where we have x and y both negative? Well, you can see, like, if you just draw your unit circle, and you see the x coordinate, so we want a negative x coordinate, negative y coordinate. So this is all the points in the third quadrant right here. So quadrant, what's this for? Oh man, I almost forgot my Greek letters. Oh no, it's just quadrant 3 like that, right? The one I just wrote before. So it would be quadrant 3. That's where that's where the y coordinate and the x coordinate are negative. All right, so for this one, we want to identify the graph of sine. So just note that the amplitude is the absolute value of 2, which is 2, and the period. Now, I'm not saying that this is going to help us, but it's just good to write everything you know down. It doesn't hurt. You never know what's going to help. So the period is going to be equal to 2 pi over 1/2, which is 4 pi. So what that means is the graph, actually look at that, it's going to help us, repeats every 4 pi. So we want to graph these on an interval like 0 to 4 pi. But you can see like this one starts repeating. So it starts at 0 and it stops at pi and it starts repeating. So this repeats too soon. So repeats too soon. This has a period from the graph. We can see this has a period of just pi. And the same thing for this one also. You can see it starts at 0 and it starts repeating after pi. So it looks like actually, and then this one too. This one, it looks like it's gonna start. Actually, this doesn't even look like a full period. And also, we can rule this one out because um, this one can be ruled out also. So far we can rule out this one and this one, but this one can be ruled out also because the sine function, when you plug zero in, you get zero, right? But this one says you get negative, you get two. So this is actually probably cosine, some probably some cosine curve. This looks more like a cosine curve. So this is going to be your answer. And look at it, it's got the right period. First of all, it's got the right amplitude. I mean, all of them have the right amplitude. They all max out at two and min out at -2. But this one's is graphed over the interval of 0 to pi over 4 pi, and it shows that the pattern is repeating afterwards. So this is going to be the right option. And also look at it goes to the origin, which is exactly what the sine curve does. So the right option is going to be D. So actually finding out the period was helpful. The amplitude didn't help us so much in ruling out options. All right, so for this one, we want to express these two in radians and degrees. So for these problems, we need to remember our conversion factors. So to convert, we need these two factors, these two fractions, to convert from radians to degrees or degrees to radians. So that you use this to convert from let's say radians to degrees, and then you use this fraction right here to convert from degrees to radians. All right, so we want to convert from degrees to radians, so we want to use this one right here. So we're going to take 3 degrees and multiply by pi radians. You don't actually need the radian unit measure, but it doesn't hurt to throw it in there. And now when you divide, so now you got 3 divided by, first of all, the degree cancels out, the units cancel, and all you're left with is the pi, right? The radians. So, um, and then this should be, I guess, it should simplify to pi over 60, I guess. Yeah, that should be pi over 60. Okay. All right, so that should be pi over 60. And so that finishes that one. And now in this case, we have notice there's no measurement, so there's no degree measure, so you're gonna assume it's already in radians. We're gonna assume that this is in radians. So what we want to do is we want to convert from radians to degrees. So we want to use this conversion factor right here. So it's gonna be 4 pi over 3 times 180 degrees over pi. I'm gonna drop the radian. So now in this case, we got this pi cancels with this pi, and then this 3 cancels with this to give us 60 degrees. But then we have the 4, so it's going to be 240 degrees. Let me just use a calculator just to check. So convert 4 times pi 32 degrees. I'm using Wolfram alpha. Uh, Actually, that didn't work well. Surprising Wolfram alpha didn't work. All right, yeah, so hold on, something's weird. this should be the right answer, but Google's acting up. Okay, yeah, so this is right. All right, so for this one, we want to figure out, we have all these trig functions, and we want to calculate these trig functions at a single angle. And almost all this kind of problem almost always shows up on on a final. So you got to know not only the sine, cosine, and tangent, but you need to know the cosecant, secant, and cotangent. But it's really not hard because everything is matched. Everything is like arranged so that once you write this answer right here, you just take to get this, you just flip it. That's it. It's gonna be really easy. So just remember that this is the reciprocal of this is the reciprocal of this, and this is the reciprocal of this. And once you know that, all you really need to know how to calculate is the first line. And that's not that bad at this point. All right, so all you really need to know is how to calculate the first line and just take the reciprocal. But first of all, what is this angle? Well, it's clear that 5 pi is bigger than pi. Sorry, 5 pi over 6 is bigger than pi over 2. I want to figure out where does this angle or this parameter land on the unit circle. So on the one hand, it's bigger than 5 pi over 6, but it's also less than 6 pi over 6, which is pi. So it's between pi over 2. So 5 pi over 6 is between pi over 2 and pi. So it implies we're in the second quadrant. And so remember, when I have emphasized this in class a number of times, if you didn't, you have, for those who don't go to class, I want to emphasize now, when you go to take the exam, the first thing you want to do is write down the unit circle and those common angles and parameters, so you don't have to worry about remembering the unit circle. Get those unit circle or while you're solving the problem. Get the unit circle memorized before the exam, so that when it comes time to take the exam, the first thing you do before you solve any problems is write down the unit circle, and you have all those values there for you, so you can solve this problem in a matter of seconds. So, let me just actually pull the unit circle up so you can see what it looks like. You don't, let me see. Some of them look kind of scary, honestly, but you don't need, let's see. Let's see, try to get this open. So here's our unit circle. Um, and it looks like a lot to remember, but it's not. It really is not. All you need to remember is everything in this first quadrant right here. Hopefully you can see it. I'm circling. All you need to do is remember this first quadrant, and you notice if you look at the coordinates in the other quadrants, they're the same coordinates, but just you got to decorate the coordinates with negative signs in the appropriate spots. So you have 120 degrees. Actually, this is not a good one to memorize because this doesn't have the radians on it. You want the radians also. Um, let's see. This actually has everything you need right here. All you need to remember is the first quadrant, because you notice if you look, pi over 3 and 2 pi over 3, they basically have the same coordinates, except you got to put a negative sign on the x coordinate. So when I give you an angle, or I give you a t value or a theta value, you just got to figure out which quadrant it is in, and then look to the first quadrant to get the coordinates, and then just put the appropriate signs. Just put the negative signs in the appropriate spots. So for us, we are looking at this angle of 5 pi over 6, this t value, this theta value, however you want to think about it. Arc length, you can either think of it as an arc length or a angle. So as I said, it lands us in the second quadrant, so it's gonna be maybe like right here. So all we need to know is, remember, is the coordinates for this point right here. This is gonna be correspond to pi over 6. And the coordinates for this are they are √3 over 2, 1/2. So now if we're in the second quadrant, then we know that the coordinates of this point, so this is going to be, this is kind of cramped, but this point right here is going to correspond to 5 pi over 6, and the coordinates of it are, well, the y coordinate is still going to be positive, it's going to be the x coordinate that's negative, so it's negative √3 oops, over 2, 1/2. All right, so this point right here corresponds to 5 pi over 6, and the coordinates are negative √3 over 2, comma 1/2. So the y values, so the sine of this angle is just going to be 1/2. So cosine is going to be negative √3 over 2. And then the tangent is y coordinate over the x coordinate. And so that's going to be, when you simplify, that's going to be negative √1 over √3. All right. And now this is the hard part, just getting that first row, because the next row, cosecant, secant, and cotangent, is just the reciprocal, because this cosecant is the reciprocal of sine. The secant is a reciprocal of cosine. The cotangent is reciprocal of tangent. So we get 2, we get a negative 2 over √3, and then we get negative √3, and that's it. So not that hard. Once you know the unit circle, and you remember that the bottom row is the reciprocal of the top row, cosecant is reciprocal of sine, secant is reciprocal of cosine, cotangent is reciprocal of tangent. Then it's pretty easy to solve. All right, so now the next problem we want to figure out which of these identities does not hold. So you could actually, there's these trig identities that you kind of have to memorize, sort of, but they're like these basic Pythagorean identities. And it's going to turn out that this is the right answer. But if you don't remember them, just try plugging in some numbers and see what you get. So, let's see, is that easy? Can you plug in, let's see, what if you plugged in, let's say pi. Okay, so well, let's try to rule out no, B. Can you plug in, so let's try to rule out B. So can you plug in x is equal to pi? So do you get tan? So the left-hand side. So you can't plug in pi because cotangent is not divided by pi. So this is a little tricky, actually. Actually, no, wait, this is not bad. I'm being an idiot. Tangent and cotangent are reciprocals. Oh, okay. Wait, hold on. Oh, I see. Oh, okay. I misread the question. Which is the following equations? Which of the following trigonometric equations is not true? Oh, well, A is definitely true. B is true. This, I mean, maybe you've seen A in this form. It's gonna be secant squared x is equal to 1 plus tan squared x. This is true. B is also true. Why? Recall that cotangent of x is equal to, is the reciprocal of tangent of x. So these two cancel out. So B, you get tangent of x, cotangent of x, minus cosine squared x. Well, the tangent and the cotangent cancel, and you get 1 minus cosine x. But remember, by the Pythagorean theorem, sine squared x plus cosine squared x minus 1 is equal to 1, sorry. That implies that sine squared x is equal to 1 minus cosine squared x. So this right here is equal to sine squared x. So B is true. So B is A and B are definitely true. So that just means you can just deduce that C must be the false one, assuming that no one made a mistake writing this problem. So hopefully you can see what I did here. So A is just one of the Pythagorean identities. B follows from the Pythagorean theorem or the Pythagorean identity. This one right here. By doing this calculation, see this calculation I did right here. I know that tan times cotangent is 1 because they're reciprocals right here. And then 1 minus cosine squared x is equal to sine x. So A and B are true. So that just means that C has to be the false one. All right, let's see. So now for this one, we want to, there's another identity I should say. For this one right here, 46, we need to use another Pythagorean identity. I just want to pull it up so I don't make sure I don't screw it up. Yeah, so you have, let's see, which one's in it? I should mention that I didn't go through all of these, so uh, I got a list of them. There's a list of these trig identities. I'll show you in a second once I've isolated exactly which one is gonna be helpful. I guess actually you know what? Let's see. Let's do it this way. I think I had a better way. So secant of alpha is -2. Remember, secant is 1 over cosine alpha is equal to -2. So that implies that cosine alpha is equal to -1/2. Okay. So now what we want to find is tangent. Oh, yeah, we can just use, all right, I'm sorry. I'm complicating this. What I was gonna do is actually fine, but I'm making this unnecessarily complicated. So what we know is that tan, and this is the identity we actually I wrote here. We know that tangent squared of alpha plus 1 is equal to secant squared of alpha. So that implies that tangent squared of alpha is equal to secant squared of alpha minus 1. Now, we're told that secant alpha of alpha is -2, so when you square, you get 4 minus 1 is 3. So tangent squared is equal to 3, so that means tangent of alpha, so tangent squared of alpha is equal to 3. So that means when you take the square, you get plus or minus √3. But we're talking about angles between pi over 2 and pi. So that's going to help us determine whether or not we need to it's going to help us determine which route to choose. So what's the best way to think about this? Well, I guess maybe just the unit circle actually. So let's draw our unit circle. So we're looking at angles between pi over 2, so here's pi over 2 and pi. So we're looking at like this angle or this angle, one of these angles, it doesn't matter. All that matters is that you can see tangent is going to be negative because we're in the second quadrant. So I should say these angles correspond to second quadrant. So that means we want to take tan alpha of we want to take the negative root. That's going to be our answer. All right, so just to remind you, so let's and then finally we didn't want tangent, we wanted cotangent, but now since we know tangent, we can easily just find cotangent by taking the reciprocal, right? So it's going to be -1 over √3. So this will be the answer, actually, the final answer. All right, so let's just review what happened. So for this problem, we actually piggybacked off of this one. We used part A to write down this identity right here. Because statement A is true in number 45. And then you can solve for tan squared alpha. It's going to be secant squared alpha -1. And since secant alpha is -2, that implies that secant squared alpha is 4. And then -1 gives you 3. So tangent squared of 3, tangent squared of alpha is 3. And now to get tangent, you take the square root and get this right here. Be it plus or minus √3. Now the question is, which one is it? Is it the plus root or the minus root? Well, in order to determine if it's going to be plus or minus, you need to remember what angle we're talking about. We're talking about angles that between pi/2 and pi. So that lands you somewhere on this arc right here, on this in the second quadrant. But tangent is negative in the second quadrant because the y-coordinate is positive, but the x-coordinate is negative. And remember, tangent is y over x. So that means that we're going to take the negative root, but we don't want tangent, we want cotangent, so we just take the reciprocal to get that. So that's how you solve that one. All right. I'm gonna pause for a moment. So let me pause. All right, we have just a couple more problems. Let's try to finish these now. So hopefully you can see what I'm seeing. So we have this problem number 47. We have some information about a triangle. We don't have the complete information of it though. So so first of all, we want to find B. We want to find B. Sorry, B or C, B, and sine of beta, and then the area. So first of all, let's try to figure out what B is. So we're given that tan of alpha is 3/4. But on the other hand, tan of alpha is by definition the opposite, or the opposite divided by the adjacent, A over B. And A we know is equal to 2, so we have 2 over B. Sorry, I didn't write the 2 actually. So putting these two together, so we have 2 over B is equal to 3/4. We have 2 over B is equal to 3/4. And if you just do the algebra out, you find that B is equal to 8 over 3. So we have that B is equal to 8 over 3. Now to get C, we can use the Pythagorean theorem because we're dealing with a right triangle. We can only use the Pythagorean theorem because we're dealing with the right triangle. If we weren't, we might be able to use the law of cosines. Remember, the law of cosines is sort of a generalization of the law of sines. It's like sort of a Pythagorean theorem for triangles that are not necessarily right triangles. Of course, we saw though that if you write down the equations for the law of sines and apply it to a right triangle, the equations just reduce to the Pythagorean theorem. So it is in fact a generalization. So for us, we have Pythagorean theorem states that a squared plus b squared is equal to c squared, and we know a and b, so we have 2 squared, which is 4, and we have 8 over 3, which is 64 over 9, is equal to c squared. And if you solve do the algebra. I'm not going to do it just to save time. You'll find that C is equal to 10 over 3. So now we have C, and we can actually just get the area. We actually have, we didn't even need C, but all we needed was A and B to get the area. So the area is going to be 1/2 base. So the length of this set line segment times the height times the length of that line segment. So it's going to be, sorry, it's going to be 1/2 A times B, which is 1/2 times 2 times, oh, did I do something wrong here on my paper? Let's see. Yeah, I did something wrong. Anyways, it's gonna be 1/2 base times the height. So A is 2 and B we just found is 8 over 3. So that's gonna imply, so the twos cancel and then all you have, oh, sorry. Yeah, the twos cancel and all you have left is 8 over 3. So that gets that, and all we need now is sine of B. Well, that's not too hard to get. So imagine you're standing here. Usually when we compute angles, we imagine we're standing here and we measure adjacent and opposite relative to this point. But that's to get the sine of any other angle. It's not that hard. You just imagine you're standing here, and then when you stand here, the opposite becomes, or sorry, the side that was adjacent to this vertex is now the opposite of this one, and the side that was the opposite to this vertex is now the adjacent to this. So sine of B is going to be equal to um so we're standing here, so it's going to be the opposite, so B over the hypotenuse C, and that is going to be equal to 8 over 3 divided by 10 over 3. And then if you do all the math, you can simplify to get 4/5. So that's going to be 4/5. Sine of B is going to be 4/5. Okay. All right. So for this one, I'm going to actually not use these labels. I'm going to relabel these. So we have angles A, and then we have angle B, and then C. So the side opposite to this is going to be this one. This angle A is, so this side is length A. We have this angle here, C, the side opposite to this one is this, so this is going to be side with length C, and then this one right here is unknown. It's this side is opposite to angle B, and it actually does not matter. We won't need this. So what we want to do is we want to find the angle alpha, this angle right here. And for this, we're not dealing with a right triangle, unfortunately. So we have to use either the law of sines or cosines. And it turns out the law of sines is going to help us in this case. So always write down the law of sines because it's the simpler of the two. That is, it's the simpler of the law of cosine. That is, sorry. The law of sines is simpler than the law of cosines. So if you can use the law of sines, that's preferred. So we have that, so the law of sines says that sine of A over A is going to be the sine of B over B is equal to the sine of C over C. So we kind of want to solve for this in terms of known quantities. Well, we know A, we don't know B, and we don't know side length. We don't know the lowercase b, but we also don't even know angle B. However, we do know angle C and side length C. So the idea would be to set this equal to this and solve. So what we're gonna have is sine A over A is equal to sine C over C. And when you do the algebra, that's gonna imply that sine A is equal to A sine C over C. And you plug in, so we know angle C, it's this angle right here. We know side length A, so it's square root of 2. and then sine of 2 pi over 3 divided by side side length c, which is 2/3 root 2. And then so now just carrying this over here, this is going to be equal to root 2, oops, root 2 over root 3 sine 2 pi over 3. Now 2 pi over 3 is bigger than pi over 2, but smaller than pi. So this angle is in second quadrant. And if you have your unit circle drawn, you will realize that well, first of all, this number is going to be positive because in the second quadrant the y-coordinate is positive, and it's going to be equal to root 3 over 2, root 2. Sorry, root 3 over 2. And that will be this simplifies to root 2 over 2. And so what we have is that so what this says is that sine of A is equal to root 3 over 2. So A is equal to the sine inverse of root 3 over 2. And what does the sine inverse do? Well, it's just oh, sorry, that's not root 3 over 2, it's root 2 over 2. Root 2 over 2, root 2 over 2. So sine inverse basically says, okay, I'm going to take what the input for sine inverse is a y-coordinate, and it spits out the angle corresponding to that y-coordinate. So if you look at your unit circle, root 2 over 2 corresponds to pi over 4. And so that would be the answer. So alpha, so angle A, which is alpha, is pi over 4. I think that's all they wanted to know. Yeah. All right, so now let's jump back up here. There's something that we didn't quite really cover, so I want to cover it now. It's not really that bad, this problem. It's kind of annoying. Honestly, this is just one problem. If you can do everything else but this problem, you'll be fine on the exam. So it's kind of more or less like cost benefit analysis for you. So it's not hard to solve this problem and memorize the formula you need, but if it does take away time from studying and making sure you solidly understand all this other stuff we worked on, and it might not be worth honestly going through because it's just gonna be there's gonna be in all probability there's just gonna be one problem like this, and it's probably not gonna count for a lot. So if you have to make a decision on what to study, definitely study everything we've done over this. And if you got time, sure, work through this problem, try to understand the details. And as I said, it's not that hard. So let's go through the details of it. So basically, you just get this annoying formula. I honestly wish we didn't really teach this because it's honestly stupid. It's like it's kind of the problem is like you have to throw it in there because the calculus and pre-calculus does technically need to be an applied math course. So it's like, oh, let's just throw in this stupid applied problem so that it's like, where we can cater to the people who say we need to have applications, but it's really just a cheesy application of math. I mean, it is helpful, obviously, in everyday life. It's going to be about financial stuff, but there are way more interesting applications of mathematics in this. So that's why I don't really usually cover it unless we have to. And now it turns out we have to. So this is the formula you need to remember. So it's of the following form, and I'll explain it all the notation in a moment. So A is going to be your amount. It's going to be like the amount of money you have at a given time T. Um, T. So like you're going to deposit money and you have this interest every year and you want to look at how much you have over the year. Like as time passes, your amount is increasing or maybe it's decreasing depending on the problem. Um, but the amount is a variable. It changes with respect to time. This is a function of time. All of these other things like P, R and N, they're going to be constants, usually constants. They're going to be fixed numbers, and they're going to be like related to this 100, this 5%, and this 1 year, and compounding it every month. So these are fixed constants. It's t really that is the variable. So A is the amount at time t, P is the principal, or maybe you could call it initial amount. This equation also describes radioactive decay. It's the exact same equation. It's like, except this is going to be like an increasing, like if you look at the plot of this, it's an increasing exponential function. But exponential decay is like, it's shrinking, it's getting smaller. So but they're the same formula basically. So A is the amount of time t, P is the principal or initial amount, and then N is equal to number of times interest is applied per time period. And then T is just the number of times, it equals the number of time periods. Oops, time periods elapsed. Okay. So, in our case, we are compounding. Let's like try to figure out what everything, all the details are. So in our case, we our initial amount is $100. Oops, I always put it. I don't know. To me, it doesn't make sense to put the dollar sign in front because you don't say dollar 100s. You say $100. I think euros actually. Let me look it up. I don't want to be an idiot and say something wrong. I think the euro is on. I don't know. Maybe they do it right on the left. I don't know. That's an interesting question. Why is the dollar sign written on the left? To me, it doesn't make sense. It should be the amount and then dollar sign. It's not like right here, like we have this, it's not percent and then five. You don't say percent five, you say 5%. It should be $100. So dollar sign should be on the opposite side, on the other side. Anyways, so we got $100. Um, so that's our initial amount. And then our interest rate is 5%. So that's going to be point the five. The rate is not going to be expressed as a percentage. It's going to be represented in its decimal form. And then N is the number of times interest is applied per time, or is it time period? Yeah, time. Actually, now let me see. I have the formula over here, and I just want to make sure. Uh, I actually lost the formula. Anyways, um, so it's going to be the number of times interest is applied per time period. Yeah, that's right. So in this case, our our interest is applied every month once, right? So N is going to be 1. We're getting interest at the end of every month, and it's only being applied once every month. And then now T, which is our variable, how many time periods are elapsing? Our time period in this case is months, so we have 12 time periods. So then the formula is going to read A is 100, 1 plus 0.05 over 1 raised to the 1 times 12. And I won't go through the calculation. This is 1 times 12, which is just 12. So that's how you do that problem. It's kind of annoying. But that's the basic idea. And you just got to memorize the formula. And I'll leave it to you to decide whether trying to memorize this or focusing on making sure your knowledge of the other things is solid, is what's worthwhile, I guess. That's all we have, and I will upload this ASAP.